Hey everybody, let's talk about the basics of how to write net ionic equations today. You are all familiar with writing balanced chemical equations. So for the example of lead nitrate and potassium iodide forming lead iodide and potassium nitrate, you can write a balanced chemical equation for that. But this balanced chemical equation doesn't really tell the whole story. It shows us the chemicals that are present in the beaker, but it's not showing us exactly what form they're taking, and nor is it showing us which ones are actually involved in the reaction and which ones are extraneous. So that's what we're going to do today. We're going to talk about writing what are called complete ionic equations, where we show the chemicals in their actual form, that we find them in the beaker, and a net ionic equation that allows us to focus just on the things that changed. So I'm going to take this equation and I'm going to break apart and dissociate any ionic compounds that when you dissolve them in water actually break apart to form ions. We call those compounds strong electrolytes. Those are compounds that form ions in solution and therefore can conduct electricity. I have now rewritten this equation breaking apart any strong electrolytes that are in aqueous solution. This is actually showing us what we have inside the beaker before, or in our containers, before and after the reaction. But you'll notice there's some things that are on both sides, specifically the potassium and the nitrate, that don't change. So we're just going to omit those in our net ionic equation. There it is. What we've done with this net ionic equation is both shown what form the chemicals actually are taking. So things that are aqueous and are ionic, many of those are going to be strong electrolytes. They're going to break apart into their ions. I'm showing those ions with their charges that they're aqueous, and then I'm showing that they're forming that solid precipitate on the other side. But it's just the parts that are actually changing. And it really allows us to hone in on what's going on in a chemical reaction, and so it's super useful. You need to be able to do this. Let's talk about first, how do you decide which compounds you actually need to dissolve in water and dissociate into ions more specifically. Okay, first off, things that are aqueous is where you're going to start. If it's not aqueous, it's not going to be dissolved in water. So that's the first part. So you're looking for things that are aqueous, but then not everything dissociates fully. So not everything's going to break apart into those ions. We're looking for what are our strong electrolytes. There's some rules to make this easier so you know which ones they are. Okay, folks. Aqueous compounds that contain alkali metals, so sodium, potassium, lithium, group 1, ammonium, nitrate and acetate, those will always be strong electrolytes. These guys are always going to dissociate. You need to have these memorized. There's a couple of things you'll see that are handy to know, but you don't necessarily have to have them memorized because there are a few exceptions. Our halogens, with the exceptions of silver, mercury, and lead, are typically going to be strong electrolytes as well, and you would dissociate those without the exceptions. And then sulfates typically are strong electrolytes as well, but they have their own set of exceptions. Strontium, barium, mercury, and lead compounds don't dissociate fully. So memorize the ones that always dissociate. Got it. Now, once you've figured out what's going to dissociate, here's your process for writing a net ionic equation. You're going to write the balanced chemical equation. You're going to dissociate any ionic compounds that are strong electrolytes, that list we just talked about. When you dissociate them, you must write the charges on the ions, and you need to take note of any subscripts that were there due to charge balance. Those are going to become coefficients when this compound dissociates. We'll play with this in class some. Once you've dissociated any strong electrolytes, you're going to cancel any spectator ions to see what remains in your net ionic equation. Let's do one together. Okay, here's my equation. First thing I need to do is I need to figure out what's going to dissociate. What's going to be a strong electrolyte? Barium nitrate, yep, this guy's going to dissociate right here because of the nitrate ions. Potassium sulfate, yep, this guy's going to dissociate. It has a group 1 cation potassium in it. Barium sulfate, okay, first off, that's a solid, so it's not going to dissociate. It's not aqueous. And secondly, that's one of those exceptions to the solubility rules, so that's why this guy is a solid. Do not dissociate it. Potassium nitrate has both group 1 cations and nitrates. These guys are going to get dissociated as well. So we're going to take it, we're going to write these broken apart, all the things that are strong electrolytes. Okay, there's my complete ionic equation. I broke apart all of these strong electrolytes that were aqueous solutions in this case. Now I got to look for spectator ions, things that are on both sides of the equation and we can cancel out. So potassium and the nitrate, these are on both sides of the equation and they're going to cancel, which leaves my net ionic equation like that. The last thing I want to say, because it's what tends to trip people up on these, is that please make a note where you have these subscripts that are for charge balance. So here, when that dissociates, you get 2 potassiums. Don't change subscripts on polyatomic ions, but if they're there for charge balance, make sure that that subscript becomes a coefficient. And then when you've got a coefficient like in front of potassium nitrate, you've got 2 potassium nitrates. Remember, that coefficient applies to both the potassium and the nitrate. That's a terrible arrow, but you get the idea.